Well, welcome. When we left off, we were talking about transition metal complexes. And so to go through the previous slides quickly, we started talking about Lewis acids and bases. A Lewis acid is an electron pair donor. A Lewis base is an electron pair donor. A Lewis acid is an electron pair acceptor. We talked about the fact that, well, this chemistry shows up all over the place. It's not limited to any type of solvent. Again, here's a Lewis base, electron pair donor. Here's the Lewis acid, electron pair acceptor. And this led us into transition metal complexes. We talked about the fact that we had seen these before with a central metal ion that's bonded to six water molecules. And so on and so forth. But again, we had seen these, and these were acidic. They would lower the pH of a solution. They would act as weak acids. But we talked again more in general about complexes. We can have ligands. Ligands are Lewis bases. We have the electron pairs from the ligands are donated or bond into empty orbitals that are on the metal ions. You can have ligand exchange reactions, as was demonstrated here. The oxidation number and the coordination number are the two most important parameters that characterize a transition metal complex. We talked about, let's see, the different types of shapes that appear. So there's if you have a coordination number of 6, then you're going to have an octahedral complex. Two different geometries are common when you have a coordination number of 4, etc., etc. We got into the nomenclature. I asked you to memorize the names and the structures of some of the ligands here. And we went through a series of rules by which we would name these transition metal complexes, including the complexes that have a negative charge on them. And then we got to this slide right here. And this slide is on polydentate ligands. And ligands that only donate one pair of electrons are called monodentate ligands. And the mono means one, and the dentate part means toothed. And so we have a ligand with one tooth when it has one electron pair. And we saw that most of the ligands in this table were monodentate ligands. And so even though iodide, for example, has 4 electron pairs around it, it's only able to use one of those electron pairs when it binds to a central metal ion. It couldn't use the other ones because that would make a metal and its complex too close. So these are monodentate ligands, again, for steric reasons. Hydroxide was a monodentate ligand, as was water. Ammonia, we know its Lewis dot structure, just one pair of electrons, monodentate ligand, so on and so forth, cyanide, carbon monoxide. And again, we've got these names for all of these: amine, cyanocarbonyl, and so on and so forth. So once again, polydentate ligands exist, and not only do they exist, but they're actually really important for a variety of reasons, and we'll explore some of those. But this right here is a common polydentate ligand. It's a bidentate ligand. There are 2 teeth, as it were, here. So we've got an electron pair on this nitrogen and an electron pair on this nitrogen. And so you can get this ligand, which is called ethylene diamine. Sometimes it's abbreviated EN. But you can get it to bind in this fashion in a transition metal complex. So we still have a coordination number of 6 here. We have 6 metal atom bonds. We have 4 bonds to oxygen here and 2 bonds to nitrogen. But we have this bidentate ligand, this polydentate ligand, and we have these electron pairs that are bonding into the central metal ion in this way. So again, ethylene diamine is making 2 bonds to the metal. And again, these are polydentate ligands, and ethylene diamine is an important example of a bidentate ligand. And again, we're seeing how it binds to, I guess this is, well, I'm not sure what this ion would be, but it has a 2+ charge on it. Here's another one right here, but here we have 3 ethylene diamines. And so we still have a coordination number of 6. We can see the 6 bonds between the central metal ion and these other atoms, but there's an ethylene diamine here, and here's an ethylene diamine here, and here's yet another ethylene diamine. So we have these 3 ethylene diamines around the central metal ion. Again, well, a bidentate ligand. You should know the structure of ethylene diamine. NH2, CH2, CH2, NH2, you should be able to draw it, know the abbreviation, and then know that it can function in this way where both of these nitrogens can simultaneously act as Lewis bases. Again, these electron pairs go into empty orbitals that are on the metal ion, and we form then nitrogen metal bonds. Here's another example of a polydentate ligand. This is diethylene triamine. So an ethylene unit is a CH2CH2 unit. So we've got two of these. We've got one here and we've got one here. So this means we have diethylene. Then we have triamine. And so we've got an amine here and an amine here and an amine here. And because we have these three nitrogens, and each one has a pair of electrons on it, so I guess we could circle them again. So here's a pair of electrons, here's a pair of electrons, here's a pair of electrons. We have a tridentate ligand. We have a ligand that it's polydentate again. And so here we see this diethylene triamine, and it's right here. So we can kind of circle it like this. This is this ligand, and now we see again it's acting as a tridentate ligand. There are three bonds forming between this ligand and the central metal ion, and then we have some waters that are in the other positions in this octahedral complex. So I would also like you to know ethylene diamine tetraacetic acid. So I don't know if we're writing out the structure here. Do we write it out? Well, we probably should. So EDTA stands for ethylene diamine tetraacetic acid, or tetraacetate, if we've pulled off the protons on it. So this right here is ethylene diamine tetraacetic acid. And I know it looks like a monster, but we can break it into smaller pieces. You notice that there's an ethylene diamine part to it. And this right here is just ethylene diamine. This is what we talked about a couple of slides ago. So it's just ethylene diamine without the hydrogens on the nitrogens. And we remember acetic acid. Acetic acid just looks like this. So here's the structure for acetic acid. And we see that if we replace a hydrogen on nitrogen and then we bind the carbon to the nitrogen in this way, we're just putting an acetic acid essentially here. So I've got an acetic acid here, and I've got an acetic acid here, and I've got an acetic acid here, and I've got an acetic acid here. Or we could also say an acetate. If we pull off these protons to make this, then I have an acetate here, and I have an acetate here, so I'll circle them. Here's an acetate, and here's an acetate, and here's an acetate, and here's another one right here. But we have ethylene diamine. This is the ethylene diamine structure. Here's the ethylene diamine backbone of the molecule, if you will. And then we have tetra 4 acetates or acetic acid. So 1, 2, 3, 4, 1, 2, 3, 4 around it. So please know the structure of EDTA. It's actually quite important. And what EDTA can do is it can form 6 bonds to a central metal ion. So here we have a Lewis base, and here we have a Lewis base. And then we'll have a pair of electrons on one of these oxygens, and another one here, and another one here, and another one here. And so I have 6 possible bonds that I can form, and I do form them to a central metal ion. And as a result, I make 2 metal nitrogen bonds, and I make 4 metal oxygen bonds. And I have still an octahedral complex. I have a coordination number of 6. And this is actually kind of a remarkable molecule. It turns out that it's put into different foods in small quantities, for example. It's called a sequestering agent. It turns out that the oxidation of foods is often driven by metal ions. Many metal ions can act as catalysts. And so if I have a metal present and I have oxygen and a hydrocarbon, like maybe oil or something like that, maybe you've got a salad dressing and you've got some oil in it. The presence of trace amounts of metal, and there are always going to be trace amounts of metal in just about everything. They're kind of trace amounts of everything and everything. But that small amount of metal can catalyze the decomposition of the oil, and then you're going to have a rancid smelling salad dressing, and of course nobody wants that. And so if you put in a small amount of EDTA will go around and it will find the metal ions and will lock them up, and then they're no longer able to act as catalysts that would result in the decomposition of your food. So this is a useful preservative for different foods. And we've all eaten a little bit of EDTA when we've, again, had things like salad dressings. So let me see, how are we doing? Yeah, I think we've just got a bunch of questions here. I'd encourage you to go through these. I think they're good questions, but let's now move on to the next lecture. And this is allowing us to keep up. Okay, I appreciate those of you that read and have read throughout the semester. I think you've done quite a good job as a class. Let's again mention Thanksgiving. I know I've said it a whole bunch of times in class, but the Monday of Thanksgiving, usually I get, usually about 1/3 of the class is not present. The Tuesday of the week of Thanksgiving, about 2/3 of the class will be gone. And so again, I've concluded based on hard experience that the best thing I can do is just send out the lectures. This gives the largest possible fraction of you the opportunity to see, to view the lectures, to get the materials. So again, I will be sending out the lectures for Monday, the 21st of November, and Tuesday, the 22nd of November. And I wish you all a happy Thanksgiving well in advance. So let's see. Choose the correct formula for the following name: potassium hexacyanomanganate 2. So how would we break this down? Let's see. Cyano is cyanide. So cyano is the word for cyanide when it's in a transition metal complex. Hexa means 6 of them. So I've got 6 cyanides. I've got 6 cyanides everywhere here. I've got manganate. Okay, so I have the cation first, the anion second. So this is a negatively charged complex. This looks like it's going to be manganese in a 2+ oxidation state, because that's what the 2 here means in Roman numerals. And so I look at my charges here. I've got 6 negatives. I've got 2 positives. That must mean that I have 4 potassiums to go with it. And then we always put the cation followed by the anion. And this is the only one that makes any sense. So A is indeed the correct reply here. Okay, what is the oxidation number of the metal ion in this complex right here? Again, we should be able to break these complexes down and say water is a neutral ligand. Bromide has 2 negative charges, so I have -2 here. Overall, there's a net positive charge on this complex. So cobalt must have a +3 charge. So again, fairly straightforward here. So let's now move on. We're going to talk about something called a chelating agent, but this is really just a polydentate ligand. So bidentate means 2-toothed, polydentate means many-toothed, and just as a little aside, dense is the word for tooth in Latin, diente in Spanish, denti in Portuguese. So we can see this Latin root that gives us the bidentate or the polydentate. And polydentate ligands, including bidentate ligands, are also known as chelating agents. And so when I talk about a chelating agent, I mean the same thing as a polydentate ligand. Again, there's a fair amount of vocabulary to be learned in chemistry. It turns out that this word chelating agent comes from the Greek word for claw. I don't know Greek, but I can certainly see how if I have a polydentate ligand, it can kind of reach around and grab a metal ion, just like the claws of a crab can reach around and grab an object. So that said, let's move into something called crystal field theory. And the purpose here is to understand why it is that transition metals are colored. And this provides a theory for where the orbitals are and the bonding and where the electrons go and all sorts of interesting stuff like this. So I hope that you find this to be interesting. An example, I guess, right here is that we've got the same metal, but in one case we've got ethylene diamines around it, and it has a certain color. And here we have 6 ammonia ligands, and it has a different color. And then we have water. I guess this would probably be nickel. We have water around the nickel, no doubt, and here's its color right here. And so we see that changing the ligands around the central metal ion changes the color. And the question is, what is going on? As chemists by now, when you see something like this, you should suspect that there's been a change in the energy levels of the molecule, of the light that's absorbed and the like. And that's exactly right. And we're going to talk about how that takes place. So it turns out that these colors right here are a result of electronic transitions of electrons within the d orbitals. And as an example, chromium 3 plus has an electron configuration of the nearest noble gas, and then there are 3 d electrons that are in this ion right here. As you might imagine, when chromium 3 plus or any other atom or ion is in the gas phase, in other words, when it's all by itself, so it's all by itself, it has no ligands around it, all of the orbitals in a given subshell have the same energy. And in the chemical world, we say that they are degenerate. So degenerate orbitals are orbitals that have the same energy. I'm sure that you've heard the term before. However, when a chromium 3 plus ion is put in water and it's surrounded by 6 water molecules acting as ligands so that we get this complex right here, the energies of the 5d orbitals are no longer the same. They're not degenerate. In other words, if I can put this ion into the gas phase, and if I could probably find a way to do this, so I would have in the gas phase this ion all by itself. All the d orbitals are degenerate. They have the same energies. But when I surround this ion right here by ligands, so now I have an octahedral complex, the energies of the orbitals are no longer the same. And this is what brings about these colors. And again, we'll see in more detail why that's the case. And once again, in general, when you change the ligands around a transition metal ion, you change the color of the complex. So let's go through this theory a little bit. So what we have here is we have representations of the 5d orbitals. And now let's imagine that the origin of an XYZ coordinate system is put on the central metal ion, or the central metal atom ion here. And so what we're doing is, again, we're putting a coordinate system where the x-axis is going like this. So there's the x-axis, and you can see it's labeled x here. And oops, here's the y-axis. It should have gone straight through there. And then here's the z-axis. I did a better job with that one. And we can obviously do the same thing with all of these. So we can put an x-axis here, and we can put a y-axis here, and we can put a z-axis here. And so I've got x, y, and z axes here on each of these, around each of these orbitals. And we're going to do this because it's going to help us. I guess we can extend them back, and we probably should. So now I've got x, y, and z orbital or axes going through these orbitals. And this again is going to help us understand them a little bit better. One of the things that we see when we look at the dx squared y squared orbital, so that's this orbital right here, and each of these orbitals is different from the other, and we're going to study them in some detail so that we actually come to understand pretty well. You know, I could show you one of these orbitals and you should be able to label it. We'll get to the point that we can do this pretty well. But in any case, notice that in the dx squared y squared orbital, in this orbital right here, these lobes on the orbital are running right through the axes. So here I have the x-axis, and 2 of the lobes of this orbital are along this axis, or along the x-axis. And the other 2 lobes of the orbital are along the y-axis right here. And remember that all of this is one orbital. So this is an orbital with 4 pieces, or 4 lobes. So here's a lobe, here's a lobe, here's a lobe, here's a lobe. So the 4 lobes together make the 4 lobes together are making one orbital. All of this is one orbital, and we know that 2 electrons go in an orbital. So in the case of the dz squared orbital, we see that these 2 large lobes lie along the z-axis right here, and I've got 3 principal parts to it. I've got this donut of electron density right here in the middle, and then I've got a lobe here and a lobe here, and all of this together makes an orbital. So I guess we've said that. We've got these 2 orbitals where the main lobes lie along the axes. Again, for the dx squared y squared orbital, this is important again. These two lobes of this orbital are running right along the x-axis, and these two lobes are running right along the y-axis, whereas right here, the two lobes here are running along the z-axis. Now, let's also look and see which planes the different orbitals lie in. So again, this is my x-axis right here, and I'll extend it going back. Here's my y-axis going here, and this should be the head of an arrow right here. So the dx squared y squared orbital, this orbital right here, all four lobes, they really are lying in the xy plane. And over here, I could also draw some axes. So here's an x-axis, and here's a y-axis. And this orbital as well is also lying in the xy plane. This is the dxy orbital. But we notice something interesting about this orbital, and that is that the lobes of this orbital are lying between the axes and not along them. So for the dx squared y squared orbital, the lobes lie along the x and the y axes, whereas for the dxy orbital, the lobes are lying in between the axes. This is a very important difference. Let's look at this orbital right here. So I could draw an x-axis like this. Here's my x-axis. Sorry, it's not maybe quite as clean as we'd like. Here's the y-axis. So we have x, we have y, and now we have z. And if we look, let's see, if we look at the YZ plane, so the YZ plane is the plane that contains the y-axis and the z-axis. So in the YZ plane, we see that we have the dyz orbital. And in fact, what we see is the dxy orbital lies in the xy plane. That's what we saw here. The dyz orbital is lying in the yz plane, and the dxz orbital is lying in the xz plane. So if I again drew the x-axis here, and I drew the z-axis here, then so x and z. So the dxz orbital is lying in the xz plane. Again, it's important to see where these orbitals are relative to the axes. Again, I guess we could put the z-axis up here. And it's also important to note that just like in the case of the dxy orbital, the lobes were lying between the axes, so in the case of the dyz orbital, the lobes are lying between the axes. And here, once again, for the xz, the dxz orbital, the lobes are lying between the x and the z axes. So, once again, in the case of the dxy and the dyz and the dxz orbitals, the lobes of these orbitals do not lie along the xy and the z axes. However, the ligands, as we have positioned them here, the ligands do lie along the xy and the z axes. So here are the positions of the ligands, and again the ligands are drawn here as passing through. So the ligands are drawn as being on the axes. And again, we've seen that two of the orbitals have lobes that lie along the axes, and we have three orbitals that have lobes that lie between the axes. And one of the things that I should make clear here, and this is really quite important, is that it really doesn't matter how I draw the coordinate system. I could draw it any which way and I'd get the same answer. It's just that we put the axes here for convenience. So again, I would get the same answer. It would just be much more complicated if I were to choose to rotate this coordinate system. Again, put the axes pointing in a different direction. So this question now kind of embodies some of the most important concepts that I've been trying to get out without actually giving you the answer. So imagine that you're an electron and you have a choice. You can be in the dxy orbital, so you can be here, or you can be in the dx squared y squared orbital in this diagram. The question is, which orbital would you rather be in? And here's a hint. Think about where you would have the least repulsion from the electrons from the ligands. Okay, well, let's kind of think about this. If I were here, if I were an electron in this orbital, would I feel the effect of these ligands, of the electrons from these ligands? The answer is, of course I would. I'd be repelled by them. Electrons repel electrons. But I notice that I'm in an orbital here that is off axis. It's not on the x and the y axes. And so I'm a little bit further away from these electrons if I'm in this orbital than if I'm right here. And in fact, things actually look pretty bleak here, because if I'm an electron and I'm in this orbital, so I'm going around between these lobes, I'm this wave, and these are kind of the nodes for the wave, right? So in any case, if I'm an electron in here, I've got electrons essentially just right in my face. So I'm confined to an orbital along the x and the y axes, but I have ligands that have electrons that are directly along the x and the y axes as well, just repelling me. So this looks like a higher energy state for me than this, and it is. So I certainly don't feel the same repulsion in both of these orbitals. I feel less repulsion right here. So which orbital would you rather be in? I think we'd rather be in the dxy orbital. Again, because we're a little bit further away from the electrons that come from the ligands. So the electrons in the different d orbitals experience different degrees of repulsion from the electrons from the ligands. And so now what we can do is we can begin to see that, again, these orbitals have different energies when I put the ligands around the metal. And the reason they have different energies, again, when the ligands are around the metal, is because these orbitals are in different places geometrically. I have two orbitals with lobes that lie along the axes. Here in the dz squared orbital, again, I've got these two lobes that are lying right along the z-axis right here, and I have ligands that are contributing electron density along these axes. And so if I'm an electron trying to be in here, I'm being repulsed by these electrons. Same thing happens here again. If I'm an electron in here, I have electrons in my face, as it were, repelling me, that come from the ligands. Whereas if I'm down here in what you might call the off-axis orbitals, so I kind of like to call these on-axis because the lobes of the orbitals lie along the axes, and I like to call these orbitals off-axis. So here the lobes of the orbital lie between the axes, and so my repulsion is not as great from the electrons that come from the ligands. Now, of course, I always get some repulsion. Once we put ligands around the metal, sure, I put all this electron density around a central metal, and that makes all the electrons in all the orbitals less comfortable. But it's going to have a greater effect on on electrons in these orbitals as opposed to these ones. And so this is exactly what we're seeing right here. This represents the energy of the d orbitals in a free atom or ion. So I've got the atom all by itself, or I've got an ion all by itself. Again, it's in the gas phase. No ligands around it, nothing around it, and all the d orbitals have the same energy. They are degenerate. Now I put 6 ligands around this metal ion. The energies of all the orbitals go up somewhat. So we went from here, where on the all the orbital energies are going up. Again, this is where my 5d orbitals are now. This is where they were before. But we see that 2 of the orbitals went up more in energy than the others, and the 2 that went up most are these where the lobes are lying along the axes. This energy difference right here is called the octahedral field splitting energy. It's given a symbol of delta. Delta means a difference in something, so there's a splitting, there's a difference between this set of off-axis orbitals and the on-axis orbitals, and then we have a little O here for octahedral. So again, I get a splitting in the energies of my d orbitals when the ligands bind to a central metal ion. Once again, notice all of the orbitals went up in energy to some degree, but some more than others. These went up in energy more than these did right here. So let me just check my clock really quick. Okay, we've got about 20 minutes, I think. So once again, the chromium ion has this electron configuration. So it has the electron configuration of argon, then it has these 3 valence electrons, and they're in d orbitals. And so this would represent the electron configuration for this system right here. And so we're assuming here that this chromium ion is in an octahedral environment, so there are 6 ligands around it. I have split my orbitals, and then the question is, where do my 3 d electrons go once I split the orbitals like this? And the answer is they go down here. They go into the lower energy orbitals. By Hund's rule, we have them all with the same spin. But again, they go into different orbitals, and from Chem 105 you should be able to see that this is how the electrons would go into the orbitals. So I guess we've already said this before, this is the splitting between the d orbitals. These are the off-axis orbitals, these are the on-axis orbitals. The 3 electrons go into the lower energy orbitals as shown here. Now, this is also important. Imagine that a photon that has an energy equal to this energy difference, there's kind of this energy difference and energy gap between these sets of orbitals. But what if I have a photon that comes in with this amount of energy right here? What can it do? And the answer is, we've seen things like this before in Chem 105 and the like. We know that if I have a photon that has an energy that matches this energy difference, I could promote one of these electrons into a higher energy orbital like this. And in fact, this is what happens. The photon hits this complex, and now an electron's going from here up to here. And I started with what you might call the ground state, chromium 3+, and I go to an excited state, chromium 3+. So this is lower energy. This is now an excited state, a higher energy state. Now, we also recall from our basic physics and chemistry that the energy of a photon is h nu. So E equals h nu. We remember that this is the frequency of the photon, and this is Planck's constant. We also know that c equals nu lambda, so c is the speed of light. The speed of light is equal to the frequency times the wavelength. And so I can do just a little substitution. I can solve for nu, and then I can stick c over lambda in here, and this means that the energy of a photon is Planck's constant, times the speed of light divided by the wavelength of light. Sorry, I'm hiccuping. I just had dinner. So you'll need these 2 constants to be able to solve this equation, and I'm pretty sure that these are on the equation sheet that you received for the class. So this is the speed of light again, and this is Planck's constant. And again, it allows us to calculate the energy of a photon. Now, what we're going to talk about for a minute is color. And for those of you that don't know this, some of these things are going to seem a little bit strange, but all I'm telling you is how our brains perceive color, and it's not entirely as some of you might expect. Now, it turns out that if we have photons of a given wavelength, we perceive that wavelength. And what I mean is that if all the photons have the same wavelength, we just perceive that wavelength. And so an example I would use in class is if I have a red laser pointer, what's happening is we're creating photons that have an energy between 630 and 700 nanometers, and you just see red. So red photons are on the blackboard or whatever, or on the screen, and you see those red photons. If I have a green pointer, same thing. I've changed the wavelength of the light. Now I'm in a range of 480 to 560 nanometers. Let's say that we have 500 nanometer photons. So I'm shining the green light. I'm shining 500 nanometer photons onto the screen. Those are bouncing off the screen, and you're seeing those photons. So if you have color of just one wavelength and it hits your eye, that's the color that you see. And that's simple. That makes sense. However, the color we perceive from an object, and now we're talking about the objects around us in general, it's not the color that it absorbs, but rather the color that it either transmits or reflects. And so this is important. Many materials can absorb light. And when a material absorbs light, the rest of the light is reflected back to us. And so our brains will take all of that light and process it in a certain way. And it turns out that this is the painter's color wheel. It turns out that if one of these colors is removed and all the other wavelengths of light shine on your eye, you perceive the opposite color. I know it may sound kind of weird, but this is what you could do. If you were to take out the red light and then shine light with all of these colors here, every color but red, on your eye, it would look green to you. This is how your brain processes color. It's how you perceive color. Same thing here. If all the blue photons were removed and then you were to shine on somebody's eye, all of these photons right here, then they would see this object, or they would see orange. And so again, we're seeing the opposite color that's in the color wheel. So whatever we remove purple, we would see yellow. And so again, this is just the way our brains process and perceive color. So kind of interesting, and maybe not exactly what you would have expected. I like to do this demo, and if I were in town, we would do this demo. What we do here is we start with a solution of it's Fe3+. So Fe3+ kind of has this kind of pale yellow color right here. And the Fe3+ that we have in this solution actually has 6 waters around it. So now we're sophisticated to be able to say, oh yeah, okay, so this is really this right here. So it's not an iron 3+ ion by itself in solution. I actually have 6 waters around it in an octahedral environment. So this is what's going on right here. If I take potassium thiocyanate, and this will form a colorless solution, but if I add this to this, I get a ligand replacement reaction, and one of the water molecules is pushed out, and this thiocyanate binds in its place, and there's a dramatic color change that takes place. So I go from something that's kind of pale yellow to something that's deep red. And this happened just because I replaced one of the ligands here around the central metal ion. So what should be apparent here, and we've already mentioned this in this lecture, is that when I change ligands, I change the color. And what this means is that different ligands are causing different degrees of splitting of the d orbitals in an octahedral complex. And it turns out that some ligands split the orbitals a lot in energy. In other words, they make a big difference. They cause a big difference between the off-axis orbitals and the on-axis orbitals, and some not so much. And it turns out that whether we have a lot of splitting or a little, or just a little bit of splitting, it doesn't make any difference when we just have a few electrons. But when we have a few more electrons, it is going to make a difference. So I think we can illustrate this in the following way. So I'm going to draw my d orbitals like this. So these right here are the off-axis orbitals. This is representing the dxy, the dyz, and the dxz. That's down here. And then over here I have the dx squared y squared and dz squared orbital. They're higher in energy. But if I just have one electron, whether I have a small amount of splitting or whether I have a huge splitting, so we imagine that this is now the energy gap, my electron is just going to go into the lowest energy orbital. It's going to look like this. And similarly, if I have a situation where I have 2 d electrons, those d electrons, when I put them into these d orbitals, they're just going to do this. And I guess we could separate that out, and so we separate this here. And so now I have, if I have 3 electrons, then let's see, they just go into the lower energy orbitals like this. And so what we're seeing is that it doesn't make any difference whether I have a large gap in energy, a large energy difference here, or a small energy difference. The electron configuration is the same here. I just have 1 electron in one of the off-axis orbitals. And the same thing here for 2 d electrons, and the same thing here for 3 d electrons. But now I want you to answer this question, and it's this silly little question, but I actually really like it because it illustrates the concepts that we're talking about. So you get a parking ticket, and the city sends you a notice that you have to pay a fine. You're going to have to pay something no matter what. However, this is a really strange city, and you're given the option to pay either $5 or $50. So the question is, which would you rather pay? This is not a trick question. And the answer is, given the choice, we would all pay $5 instead of $50. Now, this leads us into the next question. So again, if you have a choice between paying $5 for something or $50 for something, you pay the lower price. That just makes sense. Well, electrons are going to do the same thing in these transition metal complexes. And so now let's consider the possibilities of having 4 or 5 or 6 or 7 d electrons. And this is illustrated right here for 5 d electrons. And what we're showing is that in some cases, when the ligands make the octahedral environment for the metal ions, sometimes you get a little bit of splitting, energy splitting, sometimes you get a lot. And it turns out that there's an energy that we have to take into account called the spin pairing energy. And the spin pairing energy is kind of just what it sounds like. It's the amount of energy, it's the energy price you have to pay to put the electrons together in the same orbital. Because when you put those electrons together in the same orbital, of course they repel. They don't like each other. They push back. And so again, there's this spin pairing energy, there's this repulsion between the electrons. It turns out that this energy difference between the orbitals, that again is caused by the octahedral environment of the ligands and causes, we have these off-axis orbitals, on-axis orbitals, we get this splitting right here. It turns out that this energy right here is comparable to the spin pairing energy. And it turns out that we can have situations where this delta value is smaller than the spin pairing energy. Okay, well then if that's the case, which price would you rather pay if you're an electron? And so we could kind of draw it this way. So this is supposed to be this right here. And let's fill in the orbitals right here. So the first electron will always go here. It'll go into a lower energy orbital. The next electron goes down here. The next electron goes down here. But where do we put the next orbital? Are we going to pair up the electrons here so I can begin to pair the electrons? Or does the electron go into a higher energy orbital? And we look down here and we say, oh, this splitting energy right here, this delta sub O, it's smaller than the spin pairing energy. Which price will I pay? I will pay the small price, and so that means that I'll put the electron up here. I have to pay a price to get it up to this higher energy orbital. I've got five electrons, and so this is what my electron configuration looks like. Now, let's suppose that we have this humongous, or this much larger splitting energy right here. So let's see. Now that we have different ligands, we've got this larger splitting energy, and now it turns out that delta sub O is greater than the spin pairing energy. Okay, so which price do you pay? You pay the spin pairing energy. That means that the electrons are going to go into the same orbital. Again, there's a repulsion there. There's a price that you have to pay, but now this price is lower than this price because this one just got so big. So the first electron goes here. The second electron goes here, the third electron goes here. We're happy with that. The electrons have gone into different orbitals. Where does the next electron go? I've got a D5 configuration here, so we can say that this is a D5 configuration in both cases. So I've got a D5 configuration, and we pay the lowest price that we have to. So I pay the price of the spin pairing energy, and now I've got these electrons that line up. And it turns out that this particular electron configuration and this particular one over here, so we've got this and this, and what we see again is that here I have the splitting energy is less than the spin pairing energy, and here I have the spin pairing energy is less than the splitting energy. These have a name, and the name of this complex right here is called high spin. And the reason it's called high spin is because I have more unpaired electrons. We remember that when we have an orbital and the electrons are paired up, the spins cancel. But when I have all these electrons that have the spins in the same direction, I have a lot of net spin. Over here I have less spin. It's true that there's spin from this electron. These have paired up and canceled. These paired up and canceled. This is a low spin system. So this is a low spin Fe3+. This is high spin right here. And so again, I get high spin when I don't have very much splitting here because again, this energy difference is less than the spin pairing energy. Once I make this energy large, then I force the electrons to pair up. So this is my low spin and this is my high spin. Notice that when we say low spin, we don't mean no spin. It's not that there's no spin at all here. There's still spin here. It's just that this one has more spin. So this is higher spin, if you want to put it that way, and this is lower spin. But again, we call this high spin and low spin. So another good question right here. In general, what color would you expect for a D10 electron configuration in a transition metal complex? Okay, well, let's think about this. What color would you expect for a D10 electron configuration in a transition metal complex? Let's assume, since this is all we've talked about, that we have an octahedral complex. So we're told it's a complex. We'll assume that it's octahedral. Let's draw the splitting of the d orbitals and let's fill in the electrons. Okay, so let's see, the first three would go down here. But what we see is I'm just going to fill everything up. It doesn't matter whether I'm doing this or I'm putting the electrons down here. If I've got 10 electrons in just 10 places for the electrons, I have filled up all the orbitals. So what color would I expect for this type of system? And let's see, what if, so I've still got some splitting here, so I've got delta sub O. What if this is equal to the energy of my photon? What if I have a photon with just this energy? Can I take one of these electrons and put one of these electrons into one of these orbitals? I can't, because these orbitals are full. What that means is that this complex right here is transparent. It will look like water. I can't absorb light because I have filled orbitals right here. I can't promote these electrons into these orbitals. So there will be no color, in fact, which is rather interesting. If you look at Zn2+, look at Zn2+, zinc 2+ in the periodic table, you'll see that it has a D10 configuration. And in fact, if you ever have a zinc salt and you put it in water, there's no color to it. You put copper in water, you get a beautiful blue solution. You put nickel in water, and generally you get a nice green solution. You put zinc in water, you have a colorless solution. And it's all because of the number of electrons that are in the d orbitals. And again, in the case of a D10 electron configuration, I can't promote one of these electrons into one of these orbitals because these orbitals are occupied. Here's an interesting question. What color would you expect for a D0 electron configuration? And the answer, of course, is, well, if I have no electrons here and no electrons here, I can't promote an electron from here to here. So I also expect to have a colorless species. And that's the case if I have, for example, titanium 4+ complexes. I don't have any d electrons, and they're uncolored. So let's end the lecture after we go through this right here. Actually, you know what? I think it might be better just to go back here and to look at the high spin and the low spin possibilities here. So let's do this really fast. So right here I have a little bit of splitting, and right here I have a lot of splitting. And again, let's just cover these different possibilities here. So how does this work? Put lines between these. So this was the D5 configuration, so let's say D4 right here. So here we have a large degree of splitting. This is the higher price. So we have 1, 2, 3, 4. And so this is going to be, well, actually, let's just put in the electrons here. 1, 2, 3. Where does the next one go? Well, now this is a small price. The spin pairing energy is the high price. And so we have the high spin configuration and we have the low spin configuration right here. This is D4. We'll do D6. So here we have a high degree of, we have a large degree of splitting between the orbitals. 1, 2, 3, and now we force the electrons to pair up. Over here we have 1, 2, 3, 4, 5, 6. So we have high spin we have low spin right here. I guess we could put a line right here as well. And then we go to D7, and let's see, we have 1, 2, 3, 4, 5, 6, 7, and then we have 1, 2, 3, 4, 5, 6, 7. So this is high spin, this is low spin right here. Let's skip ahead. I know that this lecture is going just a little bit long, but let's do this for 8 or 9 or 10 electrons. In fact, yeah, this is certainly worth doing. Let's consider again the case where there's only a small amount of splitting, and let's consider the case where there's a large amount of splitting. Let's do this for a D8 electron configuration. Okay, so I have a great deal so my delta O value is large. 1, 2, 3, 4, 5, 6, 7, 8. Here I have 1, 2, 3, 4, 5, 6, 7, 8. We notice that we have the same electron configuration. So I'll leave this as an exercise for you to do this for a D9 electron configuration and a D10 electron configuration. But what you're going to find is that whether I have a what would be a low spin configuration if I had 4 to 70 electrons, or a high spin electron configuration, is the same. So I don't have high spin and low spin when I have a D8 or a D9 or a D10 electron configuration. They're both the same. I end up with the same occupancy of electrons in these orbitals. Well, I think this has covered the material. Let me see how. Yep, we've covered the 50 minutes. I wish you all the best. I look forward to being back on Monday, and just keep up the good work. Good luck on the test. I think the test is running right now. I'll talk to you later.